this allows to a lot of exchange of information and ideas and get us thinking about things in a different way than we might normally do. So the outline of this talk today, I want to tell us a little bit about what Biophysics Collaborative Access Team, BioCAT, is, give you a little bit of history, and then talk a little bit about the rest of the program. So what are we? We operate the undulator beamline 18ID at the Advanced Photon Source Argonne National Laboratory. It's a synchrotron beamline and is specialized for the study of scattering and diffraction studies of non-crystalline biological systems. We're operated by the Center for Synchrotron Radiation Research and Instrumentation, the Illinois Institute of Technology. We're funded by NIH as a mature synchrotron facility for structural biology. We're an old facility. We've been in operation since 1998. And anyone can anywhere can come to use our beamline through APS general user proposals or in collaboration with BioCAT's staff. And one important thing to know is that as a synchrotron resource, our access to beam time is free. There's no charges for using the beamline. So where are we? This is a picture of the Advanced Photon Source. And this big red arrow points to our beamline. And we'd like to say we're a safe distance from the main building, so they don't bother us very much back here. But anyway, it's one of 4 large synchrotron facilities in the world. The other ones being Spring 8 in Japan, the SRF in Grenoble in France, and Petra 3 in Hamburg. All these things have been in operation for close around 25 years now, and they're all going significant upgrades. I'll talk a little bit about the APS upgrade at the end. So what do? We do, there's 2 main things we do: fiber diffraction and small angle X-ray scattering, or SAX. And so fiber diffraction, what we'll be talking about today mostly is muscle diffraction. And we're funded by NIH, so we're mainly interested in disease focus of these applications. So a lot of these things we're worried about is muscle regulation techniques and how these relate to heart disease and skeletal muscle diseases, including things like muscular dystrophy. But we do other kinds of fiber diffraction as well, including fiber crystallography. There are not very many people that can do this anymore, but these have applications to neurodegenerative arthritis, connective tissue, and so on. And there's a whole field of fiber diffraction imaging, where you can scan tissue samples and look at the distribution of ordered macromolecular assemblies, and look at the amount and the distribution, and the orientation of these things, and image any of these numbers. Use these to study neurodegenerative disease, arthritis, cancer metastasis, traumatic drainage, connective tissue diseases. These programs are quite small at the moment, but it's something that we can do. About 70% of our business is small angle X-ray scattering, and most of this is to doing equilibrium SAX. And this has really come in its own in the last 20 years as a biophysical technique for studying assemblies of molecules in solution. And so the big applications are complexes, but protein ligand interactions, and another really important application, SAX, is flexible intrinsically disordered proteins. And a really exciting area right now is lipid phase transitions, all these organelles that people are finding out all sorts of interesting things about. And one thing that's unique for BioCAT is time resolved SAX, where we can look at kinetics of biochemical reactions from timescales going from less than 100 microseconds up to seconds and longer. So that's our program, and so it isn't just muscle diffraction. But I think it'd be nice to hear a little bit of history of how we got going. And so a lot of people don't know that the first X-ray diffraction experiment on anything was a study of insect flight muscle back in August of 1970 at Daisy in Hamburg. Gerd Rosenbaum, Ken Holmes, and I forget what's his first name, and this started. The muscle diffraction was an extremely important in the history of developing the synchrotron radiation, the early history of the EMBL in Europe, for instance. And so there was a lot of very exciting early work that was done. Now, if you fast forward 30 years, in the early 19s, Gerd Rosenbaum, who did built the first beam lines at Daisy, designed our beam line at the 18 ID at the APS. And we first had money to start building this in 1995, and we got first light in November 1997, and we've been operating ever since. So I just want to highlight some of the collaborations that have helped establish our scientific program. And we all owe a lot to the late Hugh Huxley. He was basically the founder of field both for electron microscopy and for X-ray diffraction. Sure, there was other people doing, but he was a towering figure in these things. And I have a personal and personally extremely grateful for me because he helped make my career originally when I was working at Cornell, the McChess synchrotron, where we published the Huxley et al. In 1984 that showed thick and thin filaments are extensible. And this is later experiments done in the early aughts at BioCAT, and they're showing that a much younger Massimo Reconditi when he was doing a postdoc, and so there was time. So he was very active to quite late in life, and then later on we had several very productive years for the Vincenzo Lamar and Malcolm Irving collaboration. And one of the highlights of these experiments, much of their work is done at the ESRF in 92 in Grenoble. But there were several experiments that were done primarily at the APS, and this is one very important paper that came in 2007, where they used interference to study stroke sizes and numbers of cross bridges during first velocity curves. And so that was a wonderful time. It was exciting to have all these people, and it's nice to see some old friends back at this meeting. And this is Gabriella looking quite happy. Some of the most fun experiments I was done were with David Mon and Michael Dickinson, culminating in our paper in Nature, the molecular dynamic cyclic contract insect flight muscle in vivo. And so what this was, we were able to take live fruit flies and put them in a fruit fly flight simulator and to put their wing beats under closed loop control. And in doing so, we collected time resolved experiments of the structures in the muscle during a 5 millisecond wing beat. This was technically very difficult in those days because we had to do it stroboscopically. We didn't have time framing detectors. What was remarkable about this, we were able to look at cross bridges going on and off the target zones. Here's these things. You can see there isn't anything equivalent in vertebrate muscle, unfortunately, but you can see the heads going on and off at 600 microsecond time resolution. There's still a lot of things we don't understand about this data. One of the things is how muscles seem to turn off very, very quickly in less than a millisecond. And we still have things we'd like to understand about the kinetics of these things. And we followed this up with the late Michael Reedy is one of the great enthusiasts of our time. He was wonderful for going around and getting people fired up and doing experiments and having huge teams come to the APS to do exciting experiments. And so here's Mike Reedy and my former graduate student Tanya Bekarova in action here, and here's the group here when the late Mary Reedy as well. And so this was a wonderful study. We got a lot more details in how delayed stretch activation is regulated in insect flight muscle. And so this here's a time resolved picture of these things, and you can see this. Can you see this little dot blinking in and out? That's the 19.3 that was in the other thing. But the really important thing we could do in these things is actually see the tropomyosin movement by looking at the tropomyosin reflection at the same time. So these were skin muscles that were oscillated to induce stretch activation and relaxation. We were actually able to show that a regulation in insect flight muscle involved cyclical movements of tropomyosin at the same time the head's going on and off. And so it was very reassuring to show that that the regulation structure action, it's had the same troponin tropomyosin interactions in as invertebrate muscle, but they did not require transient changes in calcium. And so this was a very satisfying study, and that hasn't been improved on since. The other thing I want to mention is I had a long collaboration with Peter de Tom, originally at University of Illinois at Chicago and then at Loyola, working on length-dependent activation. Our first paper on these was a very early study on looking at mouse trabeculae, and we were able to show that myofilament lattice spacing actually altered the sarcomere length in isolated rat muscle. And people always assume this happened whenever I've seen this directly. This is this would be about the beamline at about the time when we were doing these experiments in the early aughts, and that's a very young looking Peter de Tom. And this later on, just before he retired from UIC and went to Europe, we did a study on intact twitching rat papillary muscles, where we were able to show using a mutant rat model with long titin, so that titin is most likely the strain sensor that actually tells the thick filaments and the thin filaments that sarcomere lengths are changing. And in our hands, we were able to see changes in both thick filaments and thin filaments in iostole associated with the stretch that implies communication pathways between the thick and the thin filaments during stretch that must be responsible for length-dependent activation. And these experiments set the stage for some of the things we're going to hear about today that's been followed up recently, but these were some of the initial ideas were put in paper first here. So I want to say a few words about the APS upgrade. The APS has been in operation for 25 years, and it was an extremely reliable machine and wonderful for our purposes. But things are wearing out, and so what they've done, they're upgrading thing to a new lattice that's going to give us approximately round focal spots that are going to be less than 30 microns, and actual ray tracing shows less than 10 microns. And this is going to be wonderful for fiber diffraction patterns. We won't have to worry about which direction the fibers muscles will be doing things. So we have 2 to 4 times more flux, which is probably about all we'll be able to handle. Useful for time resolved experiments, and we'll have easily make submicron beams for scanning diffraction imaging. And so this will be a big improvement, and we'll have a newer and more reliable machine. The bad part of this thing is we're now in a 1-year shutdown that started near the end of April in 2023 and will end in April 30th, 2024. And then there will be periods of commissioning. We'll be operating, doing scientific commissioning during the summer, and we'll be able to do some experiments, but we hope to be fully operational again in the fall. And so there will be a year period where we'll have very limited ability to do X-ray experiments, so we do have several planned at other synchrotrons. One of the things we want to do is to disseminate the technologies and get more people interested in doing muscle experiments at other synchrotrons. And we might want to talk about that later, because there's a number of opportunities that we have to do that. So we kind of talked about this, but what we really want to do is we want to we have an opportunity here to get a snapshot of the state-of-the-art in muscle diffraction, but now we're having the ability to compare this to all this exciting other studies, both with cryo-EM and single molecule techniques, and we have people from all over the world that don't often have the opportunity to communicate together, and so we'll get a nice concentrated dose of this stuff today, and we hopefully we can this will stimulate a lot of new ideas and potential interaction. And of course, it's all about collaboration these days. finding new people to work with and so on. And again, our big focus is on regulation of the sarcomere, and as Wei Kong pointed out, we're interested not only in healthy muscle, but we're also interested in disease muscle. And we will, at the end of the symposium tomorrow, we'll talk about some recent translational applications. So before I finish, I should thank the kind folks who pay our bills. This is the National Institute of General Medical Sciences, where a P30 grant is a mature synchrotron resource for structural biology, and we're part of the U.S. National Institutes of Health. So to move on, I want to introduce our Master of Ceremonies, who talked first, King Ma. He did his Bachelor of Sciences in China at Dalian Medical University, got it in 2011. He did his PhD in molecular biochemistry, biophysics, and from Illinois Institute of Technology, and I was his supervisor. And then he was a postdoc at BioCAT from 2017 to 2018. And since then, he's been a research assistant professor in the Department of Biology, and he's the beamline scientist in charge of the fiber diffraction program at BioCAT from second. And I must say that he's been a huge boon to our program. He's jumped in with both feet and taken full advantage of his opportunities, and with more than 40 publications to date, and many active collaborations. And he's been the driving force in a number of new scientific directions that are driven by technical advances that he has brought forward. And so you'll get to hear about that a little bit later. So with no further ado, I'll turn it over to Wei Kong.